Our speaker today is Stefanie Tellex. She's an associate professor of computer science at Brown University. Her group, the Humans to Robots Lab, creates robots that seamlessly collaborate with people to meet their needs, using language, gesture, and probabilistic inference, aiming to empower every person with a collaborative robot. At the same time, she's also a consultant in real-time robotics, where she works on motion planning accelerators. She completed her PhD at the MIT Media Lab in 2010, and then she was with us at MIT CCL, where she did the postdoc, focusing on creating robots that understand natural language. She has won multiple Best Paper awards, including Best Student Paper at CGIR and ICMI, and a Best Paper at RSS. At the same time, she has received many awards for her career as a whole, including the DARPA Young Faculty Award, a NASA Early Career Award, and an NSF Career Award in 2017. Her work has been featured multiple times in the press, including on NPR, the BBC, the MIT Technology Review, Wired, as well as the New Yorker. Finally, she was named one of the Wired UK's Women Who Changed Science in 2015 and listed as one of the MIT Technology Review's 10 breakthrough technologies in 2016. Let's hear from Stefanie Tellex.
Okay. And this talk is going to be about making robots that understand complex language in partially observed environments. So we're going to talk a lot about the complex language part and a little bit less about partially observed environments, but some. And the goal is to make it all happen. We're not there yet, but the goal is to make it all happen at the same time. Complex language in partially observed environments. And I like questions. And I tend to talk a lot and talk fast. So please ask questions and we'll figure it out in terms of how to make me stop talking so that you can get your question in. I think that you have to be a little braver to ask a question in this setting, but you should do it anyway. Okay. So this is a picture from back when I was working with Seth Teller and Nick on a robotic forklift project. And it's an incredibly exciting time in robotics because, at this time, this autonomous forklift was very much a research project. But now we're seeing tremendous success and advances in autonomous driving. And, people get all bearish on it, like, because Starsky Robotics just closed, and that was a autonomous trucking company. But, some companies are good and some companies are bad. And if you look at what Waymo's doing, like, oh my gosh, there's a tremendous amount of progress happening in autonomous vehicles. There's a huge number of advances in drones. So this is the Raspberry Pi Python drone that we built in my lab. Actually, Josh Roy, who's on this call, was one of the lead developers for this platform. And it was inspired by the Duckytown project that came out of MIT. And the idea was to make a low-cost, fully autonomous drone that does probabilistic robotics, all on board the drone, all in Python. So this drone costs $225 in parts. And it does the things I thought were important in probabilistic robotics. So unsated Kalman filter, localization, and mapping, SLAM, on board the drone implemented in the Python programming language. And we're using this to teach students about drones. So we just finished the 3rd year running of our college course where each student gets their own drone. And we've now gotten funding from the NSF to purchase 300 drones from China, which is actually, and one of the reasons I'm hopeful about the world today is that that's moving forward. We are still expecting to get those 300 drones. And we're reaching out to every public high school in Rhode Island and a few other places as well, including CRLS here in Cambridge. I live in Cambridge. I don't know if you guys know that. I work in Providence and I live in Cambridge. I'm talking from Cambridge right now. So we're also reaching out to Cambridge Ridge and Latin High School to have them run this a high school version of this drone curriculum. So this is sort of educational drones. And it's really nice it's on board for education because you don't have to install ROS on your base station. Your base station laptop only needs to have a web browser and an SSH client. And that means you can use a Chromebook. That means you don't have to say, Mom, can I install Linux on your laptop? You can just use the existing laptop with no installation requirements and have them SSH into the drone, and suddenly they're doing ROS, they're doing Python, and they're learning all the stuff that they need to learn to become roboticists like all the people here. So this is educational robotics. But I also like to point to Skydio. This is a drone company. Probably many of you know about it. It's an MIT spinoff. It's located out in California. And they made a drone with 13 cameras, a stereo pair for each of the 6 sides of the cube. And this drone is capable of autonomous flight, so it can see and avoid obstacles. It can follow people in complex environments. And if you've ever seen the videos from them, they're just absolutely jaw-dropping. And critically, they have SDK access. So there's an SDK so that you can programmatically tell it what to do. So drones are really advancing very quickly right now. There's a lot of advances in autonomy for drones. So as robots become more autonomous, there's a real question about what it's going to be like to have them in our homes, interacting with our families. And really the focus of my research, how are we going to tell them what to do? So this is my son when he was, I guess he was 1. He is 7 now, and he's here. So if I get interrupted, I apologize in advance. So there's a real question of like, how are the robots going to interact with people, and how are people going to tell them what to do so they do good things and not things we don't want them to do? Existing interfaces, and again, I'll show a picture from back on the forklift project, fundamentally boil down to touchscreen interfaces. So there was a tablet interface for the forklift. This is a picture of it. There's also tablet touchscreen kind of interfaces. If you get in the back of a Waymo car and you go for a ride, there's a touchscreen interface to tell it where to go. And there's a phone app for the Skydio. So there's a phone interface for the Skydio to tell it what to do. Instead, what I think about is ways of making robots understand natural language commands just as if you were talking to another human being. So we'd like for the person to say in words things like, put the metal crate on the truck. And then the robot has to figure out what those words mean, what metal crate means, and map it to very high dimensional, noisy sensor data that's coming in, and figure out like what the metal crate is, and then produce very high dimensional control outputs to the actuators that that robot has. And this is challenging on its own just because it's complicated to go from this very low dimensional language space to the high dimensional inputs and outputs of a robot's sensors and actuators. It's also complicated. Wow, the videos kind of work. The people in the job talk were having troubles with their videos, but I didn't take my videos out, so yay. I can tell because I'm watching this talk on my other laptop. I'm presenting on one, so I think I see what you see. So here's a video of the forklift in simulation putting a pallet on the back of a truck. And what we did to collect data, and this is what we still do. So I share this video because it's the same data collection methodology that we've been using, since for 10 years. We show some representation of the robot's action. And then we ask people, Turkers on Amazon Mechanical Turk typically, we ask them, how would you command a person to carry out the action that you see in this video? And they say things like, put the tire pallet on the trailer. They say, place the pallet of tires on the left side of the trailer. So here, they were more specific about where the pallet should go. And they say, lift tire pallet, move to an occupied location on truck, lower tire pallet, reverse to starting location, lower forks, end. Frequently, when I give this talk, I get a laugh there, and I have no idea if I got a laugh from you guys. Probably not, because there's like this social laugh effect that is totally missing from this modality. Okay, so they made this sort of funny programming language thing to talk to the robot. But a human, if you were trying to sort of follow that command, you'd be able to understand that, and they gave a lot of detail here. And we actually did this, a lot of times for this particular video. And what we see is that no two annotators gave the same command, even for that relatively short video clip that you saw there. And what the challenge is, and the challenge that we're still grappling with in my group, is how can we be robust to all of this linguistic variation? How can we understand commands that people give to robots, no matter what they choose to say to the robot, no matter how they choose to say it? So here we're thinking about this one command, put the metal crate on the truck. But you also want to give really fine-grained commands, like move backwards 10 feet. Or really high-level commands, move everything from receiving to storage, and have it run off and execute that command autonomously for a long time. We also want the robot to be able to resolve ambiguities when it's trying to understand these commands. So if you say, put the metal crate on the truck, and there's two trucks, so the robot's not sure which one you're talking about, you'd like the robot to ask a question, like, which truck, in order to resolve the uncertainty for what's going on. Fundamentally, the problem that we're grappling with is that people want to talk to robots about everything they can see and everything they can do. Everything. And what that says is if we really want to handle this problem, if we want to tackle this problem, we need some kind of model of everything the robot can see and everything the robot can do, in order to be able to map between language and all of those things. So the high-level contributions of what my lab is doing is we're enabling human-robot collaboration by learning decision-theoretic models for communication, action, and perception. So we need models for action because that's everything the robot can do. And we need models for perception because that's everything the robot can see. This is going to allow us, by learning these models, we're going to be able to scale to really big problems. Problems on the size of everything that a person might want to say to a robot. We're going to, by taking a decision-theoretic approach, we're going to be able to detect and recover from failure. And by learning and detecting and recovering from failure, the goal is to be able to improve from experience, to create very robust models that can understand anything a person might say. So the high-level approach that we'll take is POMDPs. Frequently, I ask if people have heard of these before, and I ask you to raise your hands. I don't know if that's really going to work, though. I'm just going to assume that, I think I'm going to assume that you mostly understand them and just buzz through. People are, is that hands raising? Oh, yay, it worked. Okay. Yay, you all did raise, okay. Some of you raised your hands and most of you did not raise your hands. You could either not be paying attention or you don't know about POMDPs. Okay.
Raise their hands.
What's that?
If people that raise their hands could lower their hands, or I'll get crazy knowing who has it.
Thank you for trying in this complicated virtual setting.
Next time you can yes option maybe.
Yeah. So POMDPs, partially observable Markov decision processes. So the idea is that there's states, a sequence of states. Each state depends on the previous state and the previous action that controls what happens in the next state. And then at each state, you get to observe something about the world. So that's your observations. These are shaded in to indicate we get to see the observations. We don't get to see the state. And then we get a reward. So we get to know when something good happened because we got a cookie. To get the reward, we might have had to do a bunch of things in previous time steps to finally get to that state where we got the reward. But there is some kind of feedback, or alternatively, some kind of representation of the goal that the robot has. So people frequently get nervous about POMDPs. And also POMDPs were sort of introduced to the AI community by Leslie, hi Leslie. If you didn't raise your hand because you didn't know about POMDPs and you're at MIT, you should learn about them because Leslie kind of made them happen. in AI and robotics. And they're a beautiful model. People get really worried about them because they're computationally intractable. They're in fact undecidable in the general case to solve them. Solving them means finding a policy, a sequence, a mapping of states to actions that maximizes your reward over time. So doing that in general is really, really hard. That said, they're the simplest model I know of that captures everything that a robot is, because there's actions, there's observations, there's states, and there's goals. So the game that we're all playing is to take this very general model of POMDPs and try to figure out specific representations, factorizations, independence assumptions, and computational tricks that we can play in order to make learning and planning tractable in this kind of approach. So what we're trying to create, what my lab is trying to create, is something I call the human-robot collaborative POMDP. The specific POMDP that captures the variables, independence assumptions, pre-learned information, abstractions that we need in order to enable human-robot collaboration. So the first thing that we're going to do is change our state representation to have a part for the physical state and a second part for the human mental state. And a key research question that my lab has been addressing is how are we representing the human mental state? For a lot of our work in command understanding, we assume the human mental state is something that the human wants the robot to do. It's some kind of goal that the human has for the robot. And we've been exploring successively richer and more powerful formal languages that we can use to represent the goal that the human has for the robot. These formal languages pose problems both for planning in the MDP and POMDP setting. It's hard to efficiently find policies that satisfy goals that are complicated. So there's planning challenges. And then there's also learning challenges. So if you're trying to learn to go from English to Robotics, one of these formal languages, there's real challenges because it's hard to get data. There's no native Robotics speakers. So it's really expensive to get data that represents the parallel data of English and Robotics, which is sort of what the deep models want. We've released some of the largest ever data sets of English to LTL, one of the languages we've been working with. But even those are on the orders of thousands, whereas the deep learning people like hundreds of thousands or millions of examples. So this is a big challenge that we're facing in robot learning. Then we can change the reward function to be do what the person wants. And we can do this in an MDP way or a POMDP way. So this POMDP way that I'm showing is sort of the way I think we should be doing it. Like in general, the human mental state is a thing we don't get to know. The reward is do what the person wants, and you're trying to estimate what they want, and then once you figured it out, you're trying to do what they want. But frequently, we'll simplify this to an MDP setting where the language maps to a symbolic expression representing what the person wants. And then that is the goal that the agent's trying to achieve in an MDP setting. And then we don't think about the uncertainty over what the person might want. We'll just do sort of a one-shot best guess to get that symbolic expression. And then we try to handle the planning challenges that are posed there. Okay, so then we get observations. So in general, all our observations come from physical sensors, cameras and microphones and stuff. But we're going to kind of privilege observations from people. So language of the person talking to the robot and gesture, for example, pointing gestures and the like. So then we can think about these parts of the model going from the model that goes from the physical state of the world and the human's mental state to generate language, and the model that predicts how the robot's actions are going to change the physical state and the mental, especially the mental state of the human, and especially communicative actions like asking a question. And that's what I think of as communication for collaboration. Then you can think about the planning problem. So the challenge of language and the power of language is that you can kind of pick out with language anything, any part of the robot system. And this is sort of orthogonal to the goal of having a small, compact planning space that you can efficiently find plans in. Because at any time, you could sort of break out of the space of the sort of box that you drew around the smaller space and jump into some other space. So we need representations for planning that are robust to that. In particular, we think a lot about compositionality and abstraction in our action representation in order to enable both more efficient planning, but also enable us to map more effectively to language. So that's what I think about as action for collaboration. And then finally, we need to think about perception. So the challenge with perception is that people use language a lot to guide where you're supposed to look for stuff, to help make perception easier. So one of my favorite examples of this, I call it the speck of dust problem. Robot, pick up the speck of dust that's on the floor. So the robot's then supposed to like look around on the floor and find the speck of dust and pick it up. Before you said that command, before you said pick up the speck of dust, you really better not have been paying attention to all of the specks of dust all around you, because your brain will explode. More formally, you'll run out of computational resources to represent all of the possible specks of dust in the world, just in case the person talks to you about them. Instead, language has to feed into the perceptual system and tell the perceptual system what to pay attention to. So before you talked about the speck of dust, you better not pay attention to it. But afterwards, it better be the most important thing in the robot's goal space. And that's what I talk about as perception for collaboration. Okay. So I always worry about not not having enough material, and then I always have too much material. So I hit these slides and then I panicked and put them back in right before. So I'm going to skip this. This is an example of the robot asking to do referring expression resolution. You can read it. Here we go. You can read it. So I'm getting some lag, but I think it's okay now. You can read that paper if you want. All these papers are on my website. So the sort of first concrete piece of work that, first of all, that was all really, really high level. Are there any questions right now before we dig into some specific papers, like the meat of the talk? I think I may demand a question, because it's really weird just talking in my room with no feedback. So somebody ask me a question. There's 102 of you. One of you
Leslie. Wait.
Hi, Leslie.
Hey. So in your model, the human is oblivious to the robot in some sense?
In my fully POMDP dream model, what I really want to have is some version. Do you know the iPom? You know how there's like two iPOMDPs? The bad one, the one that has like the POMDP, and then the other person has like a version of that POMDP, and they wrote all that math out, and they're both by Doshis, but they're different.
Trashevich.
Yeah, that's the one.
Yeah.
That one is bad, but then I guess we're at MIT, so people can know about like probabilistic programming. What I really, really, really want somebody to do is make a probabilistic programming POMDP where you can actually have like the recursive model inside, so that the robot is modeling what the person thinks, and then the person is modeling like what the robot thinks of the person, with the right levels of recursion and the right ways to back out, so that you get both of them thinking about the other person. But frequently we say forget all about that. And I also think okay, now my brain crashed, but the thing that that George and the weird POMDP thing where there's multiple agents and
the DEC POMDP.
DEC POMDPs, thank you, sorry. DEC POMDPs. I think DEC POMDPs are a little wrong.
Well, they're not appropriate for this case, I think.
They're not appropriate for this case. That's right. Because in DEC POMDPs, the agents actually it's actually, even though I know they're like officially harder, they're kind of easier because the agent gets to collude in advance on their models. They get to know what the other agent's model is, and they get to agree in advance that their models are the same, and then have a policy so that afterwards, when they're running, they don't get to communicate anymore. But then they, the optimal policy usually works out so that they decide to communicate. But the human and the robot, they definitely don't ever have a time when they know, when the human knows what the robot model is and the robot knows what the human's model is. They're always trying to figure it out.
Right.
One of the things I hope happens is that the right sorts of computational abstractions, compositional abstractions, will be able to use as hypotheses about what might be going on in the person's mind. So we're nowhere near doing this yet, but like one of the things the Army really wants us to do is to have like, complicated plans where the humans and the robots are making plans together. And what I think we need to get right is like a representation for those sorts of plans with hierarchical compositional abstraction and with a rich goal representation. And then I think you'll be able to do a version of localization where maybe you assume you know the language of plans or the space of possible plans, and you're trying to estimate what plan the person has. And SLAM, where you like, maybe you know something about you might know some things, like there's going to be some compositional abstraction, but you don't know what the actions are, let's say. And you're trying to figure out both what the actions are, what the abstractions are in the space, and also what particular ones the person has in mind through sequences of dialogue.
Okay, good.
Okay. But a lot of what we do, and a lot of the work I'm going to tell you about now, we go back to MDPs and we say, okay, we believe in POMDPs, and the work I just skipped was POMDPs. But we don't yet, I feel like we're actually almost there. But 5 years ago when I started, it was like, we don't yet have a formal language that expresses, even in like robot ease, everything that we can think of to say to the robot. And so then we go back to the MDP setting and we say, okay, well, let's just pretend that the goal is, that somehow a goal comes in robot ease. And then typically, there's some deep thing. We do the deep thing, and we learn to go from English to that language. And then we try to solve an MDP to satisfy that goal, and we increase the complexity of the goal language. And that's what I'm going to talk about now. Okay?
Good, thanks.
Cool. Thanks, Leslie. And if there's more questions, please stop. Yeah.
Yeah, so I have a question regarding the perception part of the robotics. I'm just how are you actually managing the noise removal part? Like if your robot is working in a noisy environment, how do you actually
So what I really want to have happen is that the problems of motion planning, of localization, of SLAM become abstract actions in that, and abstract observations and abstract belief updates in this giant POMDP that is running the robot.
Okay.
So I don't want to reinvent SLAM and motion planning and localization. I want them to be part of that sort of POMDP. And we've only made small steps in that direction. One of my favorite papers was Nick's paper from, I don't like to say ages ago because that makes me feel old, and Nick isn't even here, but it might make him feel old, but it was from a long time ago, about coastal navigation, which is sort of using a POMDP kind of approach to enable the robot to choose actions to navigate through an environment that made it less likely to get lost. So, and the sort of policy it came up with was to sort of stay near the coast, the walls, instead of going out through the middle of the room where it would then lose localization. Okay. Those are the sorts of things I think will come out of the right kind of POMDP model. And we have a paper that was at ICRA last year, and then another version, a 3D version that that's under review, where we're planning to search for objects. We're making plans to find an object. We assume that we have a fan-shaped sensor model and a noisy detector that can see the object, but there's some noise, so it might miss it and it might give you a false detection. And then the POMDP model is driving the robot to decide where to go in order to search for the object.
In this particular paper, are you working with the visual sensors or the speech perception part?
This paper used visual sensors, so we used AR tags as the like we had it on a maybe I don't know if I should skip to it or not. Yeah, we had AR tags on a Kinect on a Movo for the robot demonstration, and then it was searching through kind of household. It was in our lab, but a household environment in our lab to find objects with its sensor, and then we had also simulated results.
Okay, but I was actually curious about are you also working in for example, there are many people giving commands to multiple robots, how the robot actually figures out which person is speaking to that particular robot or not, right? In that thing.
A lot of what we do person one robot. We don't do much with figuring out which robot is supposed to do it. I do think that's interesting, but our hands are full with one. Okay, so I'll go on, but please stop me again if you have more questions. So we want to be able to understand commands at different levels of abstraction, right? Like high-level commands, medium-level commands, low-level commands. So what we're going to do is think about natural language commands at really low levels of abstraction. So you might say something like go down 5, right 5, 1 up, right 4, down 1, left 1, and up 3. And you'd like to be able to say that. It sort of sounds hard to understand, but you'd like to be able to say that to the robot and how to do it. You'd also like to be able to say, take the red chair to the blue room. The challenge is if you only have these low-level instructions about going down 5 and right 3 or something, they don't scale to really big environments. For example, here's the International Space Station. On the other hand, if you only have the high-level instructions, you can't even say those low-level commands like go south or go down a little bit and stop. We'd really like to say both of them. And if you just kind of naively throw them both into the action space of the robot, what happens is the robot kind of gets lost. It doesn't have enough search space to search for high-level commands in the low-level space. So in prior work that was doing this, you basically had one fixed space and you learned a model that mapped from English to a symbolic expression representing the goal for the robot, and then it would go off and do it. In our work, we changed to use neural networks to go from English to the symbolic representation, and we used a hierarchical planner that had representations for abstract commands and also for fine-grained commands. And the RNN network had to not only predict what the expression was in the formal language, but also what granularity the system should be searching. So that argmax is over both the reward function and also the level of abstraction. So what that enables us to do is kind of change our action representation into a hierarchical representation. And then we can put this on a robot and it can understand commands like go to the red room. Here the rooms are represented by tape on the floor. So it's in the blue room because of that blue tape, and it's going to the red room. And then the same model with no cone changes can understand something like go south, 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 which in this case corresponds to the same action. It's going to turn around and go. So these aren't the only kinds of commands we'd like to understand. We'd also want to understand what we've been calling non-Markov commands. These commands are non-Markov in the natural MDP for the robot, in which the state includes only the robot's current position and not the whole history of the previous positions. They are Markov if you get to have the whole history. So for example, go through the yellow room to the blue room. If you're only allowed to look at the robot's current position, yeah, you can see that you're in the blue room, and so you should get a reward. But
yeah,
you
I can hear you. Sorry. Let me just drop.
Did I drop?
I can still hear you.
Okay, I'll keep going. So you're allowed to. You don't know how to check if you've been through the yellow room to get there, because that's the whole point of Markov, right? That you didn't. How you got to that state didn't matter. Of course, you could add the whole history to the state, and then it would become Markov, but then your state is ginormous. So you have real computational challenges with this. And yet, these are very natural commands. We'd really like the robot to be able to understand these sorts of commands with constraints. So the solution that we came up with is to use a representation that can handle these sorts of expressions, LTL, linear temporal logic. And the sort of idea behind LTL is it's a logic that has expressions like finally and eventually, next, until, globally, basically always, that talk about not only what happens now, but what happened in the past. So you can have expressions that map to a sequence of states in your MDP. But the catch is that to evaluate the truth value of these expressions, you need that whole sequence of states. And if you save the whole history, you're in big trouble, because the size of your state space and therefore the size of your planning problem gets really, really big. So what we did is, I'm going to jump forward a bit, is leverage some work that Michael did, geometric LTL, where you take, you have a deep model that goes from English to generate an LTL expression. And then you crunch that LTL expression to get a finite state machine that is specific to that natural language command. It's not the whole, all possible natural language commands. It's only the one that you're responsible for following right now. And then you collide that with the underlying MDP. We call that the environment MDP at high speed. To get this larger MDP with extra states that come from the specification MDP. The label specification sort of comes from the use of LTL and formal model checking. So the language command is the specification that the robot's supposed to be satisfying. This crossed MDP contains extra states, but just enough extra states in order to evaluate the LTL expression you're responsible for. So if you're supposed to go through the yellow room, it'll remember whether or not you've been in the yellow room, but it won't remember the entire history of all the places that you've been. It's just going to save enough information to evaluate that LTL expression. And we basically did this and it worked. So I'm going to skip the detailed evaluation. This was in an RSS paper in 2018. And we had a data set. At the time, it was the largest ever data set of English mapping to LTL expressions. We worked really, really hard to annotate natural language sentences with LTL. It's really hard for the annotators, the Turkers, to do it because we would want them, for example, to say, go to the yellow room and avoid the green room. And instead, they would say, go to the yellow room through the blue room. And those would both map to the same trajectory, but the different LTL expressions. And so we had to do a lot of work to go back and correct the LTL and make sure it was right and stuff. So that was painful, but we did it. And this, like I said, was the largest data set of LTL mapping to English that we were aware of. And then we had to do also a lot of really ugly hacks to teach the deep model about the grammar of LTL. But we have better deep models now. So now we have deep models that don't generate ungrammatical LTL expressions. I think I'm going to skip the video. Okay. So then at last year's RSS, we basically combined these two papers. So the LTL paper couldn't do abstraction and the abstraction paper couldn't do LTL. And of course we want both. We'd like to be able to give high-level commands and low-level commands, and we'd like any of those commands to involve non-Markov language, things like avoid, go to the green room, avoiding landmark 1, go to the landmark 1 through the red room. So my postdoc, Yoon-Soon Oh, who's now at KAIST in Korea, wrote a paper that enriched the representation for robot ease to capture both state abstraction as well as non-Markov specifications. And this was primarily a planning problem. So the language model going from English to LTL was pretty much the same and was pretty much seek to seek, sequence to sequence. But the planning was problematic because you basically had to be fancy about deciding what level of abstraction to do your inference in. You had to do it at the lowest level that appeared in your expression. So you have to do a similar trick where you make an automata for the LTL expression and connect it with the MDP at the right level of abstraction. I'll skip the video also. Okay, so at the future directions that we're going in with this work. So what we're working towards now is making the language work more robustly in realistic environments. So Brown has weird art. It's kind of known for that. But Brown also has weird art. This is an example of a weird art on our campus, the big blue bear. I haven't seen it in a long time because I haven't gone to work in a long time. And the thing about these weird landmarks is that you'd really like to say to the robot, fly to the big blue bear or avoid the big blue bear. But for all of the work that I've shown you and most of the other work you see in robot language, the robot would only be able to fly to the big blue bear if it had previously been trained on a data set on Brown's campus with the big blue bear around so that it could learn something like landmark number 6 maps to big blue bear. But actually, this is OpenStreetMap's data. There's a lot of data, especially about weird salient landmarks like big blue bears with lamp shades in their heads. So this is the OpenStreetMap data for that part of Brown's campus with that weird bear. And you can see it's called untitled lamp slash bear. So what we wanted was for the robot to be able to use data from OpenStreetMap in one of these models so that you could take your Skydio drone to any place where there was OpenStreetMap data and give it natural language commands like go to the medicine store and have it be able to figure out what it was supposed to do. So what we used is a deep net approach called CopyNet, where the representation is basically finally, and then I don't have a close paren there, but like finally be at the landmark that's open quote medicine store close quote. And it's actually learning about what to copy and when it finds these out of vocabulary words. So then we can, so it can do this even if it's never seen medicine store or big blue bear before in the input. And then we can pass that to a module that can resolve these landmarks. So we just did something simple with cosine similarity, although in the general case you could learn a model that figures out that medicine store, the cosine similarity vector of medicine store, and the OpenStreetMap features for CVS and Walgreens were sort of the top two results. And then it reduces to the sort of same kind of problem we were doing when we had gotten to train on that data. We did a user evaluation where participants gave natural language commands to a simulated drone in Tulsa, Oklahoma. None of our training data was from Tulsa, Oklahoma. And the system's able to get these commands correct 76% of the time. And we see errors from sort of these different sources. So it actually works pretty well at we did this in simulation. There's FAA rules about flying, and we didn't get our bit. If you're a student, you can do recreational flight, but if you're not a student or you're doing it for research, then you got to get that. You have to take that test. None of us took the test, so we did it in simulation instead of taking the real Skydio there. And we showed that we're able to understand commands in cities we've never been to. So this was really exciting to me because it's like this dream of like, you open up your robot, you take it out, you launch it, and it can just understand commands as long as there's OpenStreetMap data. The other thing that's holding us back, and
Hi, sorry, I have a quick question about
Hey, Josh.
Oh yeah, I'm Josh, by the way. So can you talk a little bit about the distributions of the data sets? Like, so specifically if you're always trying to fly to medicine stores, for example, the medicine stores will be there wherever, but Big Blue Bear is kind of unique to Brown. Can you talk about that?
Yeah, so this would work for Big Blue Bear as well. Because the thing, as long as the landmark resolution model can, the critical thing is that the landmark resolution model is trained only from large text data sets. And we have lots of large text data sets. So as long as the OpenStreetMap metadata has good stuff and the human used good words, where good means that the really big language model that was trained on like the whole internet and stuff can do a good job, then the cosine similarity will be small and it'll generally figure out the right landmark. Does that make sense?
Yeah, that's great. Thank you.
So it did work for, but I wanted them to use Big Blue Bear in the paper. I think that what happened is we ended up training on Brown's data set. And also it felt like, well, Brown is us. So of course we made it work on Big Blue Bear. So it wasn't as impressive as like Tulsa, Oklahoma. But then anyway,
Thanks.
but it definitely did work on Big Blue Bear. Okay. So the other thing that I'm really excited about is training without LTL at training time. So I can't talk too much about it because it's under review, but we have a really exciting paper that is able to learn to go from language to LTL with only trajectories at the training time. And that's super exciting because that means we don't need to go through all of this pain to annotate LTL expressions that go with English commands. I can figure that out from training. And the slides I skipped are about how the NLP community actually went through a very similar evolution of their training process on the GeoQuery data set. At first, they needed to have the LTL the equivalent to LTL expressions at training time, and even more than that, they needed parse trees and stuff. But then at the end, they stopped. Okay. So I don't really have time to talk about this. This is the object finding paper that I mentioned that the person asked a question about. The idea is that you are equipped with a fan-shaped sensor model. This is showing the belief state in the environment, and then the robot's doing belief updates based on a fan-shaped sensor model and a detector. And we introduced in this paper, I was really amazed, like nobody had done, Michael did MDPs, but nobody had done POMDPs, object-oriented POMDPs. So we did them, and then we generalized POMCP to POMCP, object-oriented POMCP. And we showed that you could use this algorithm to efficiently find a policy to look for objects. And my favorite thing is that the person could lie to the robot, and the robot could figure it out. So that's this curve on the far right, where here we're showing on the y-axis. Can you see my mouse? You probably can't. Now I bet you can see it. Yes. So that's this y-axis. This is the reward. That corresponds to how quickly you find the object. And then the different colors are different algorithms. So the red one is random, and the purple one is regular POMCP. And then all of these ones up here are variants of our algorithm. And then the blue one is like a cheating baseline. The blue one gets to know where the object is in advance. So it gets to go straight to the object with no uncertainty to provide a way to calibrate what that reward is supposed to mean. So nobody can be as good as the blue one. Okay, and then the x-axis here, if the sort of base case is the person tells the robot nothing, and then the robot's just got to search through the whole room. But then the person could tell the robot something ambiguous. They could say it's in the kitchen or it's in the living room. And then the robot's got to figures out that it has to look in both places. So that's better than nothing, but not as good as the robot telling you, as the person telling you it's in the kitchen. That's almost as good as knowing right where the object is with the size of the detector that we used. But then my favorite thing was misinformed. So if the person lies to the robot and says, it's in the kitchen, but really it's not, the robot will go to the kitchen and look, and then it'll just do its belief update. There'll be some noise, there'll be a little noise model, and it'll be like, oh, I guess you were wrong. And then it'll go find it somewhere else. So it'll still earn a lot of reward, less than the informed case, but it'll still eventually find the object. So I liked it because the human can lie to the robot and the robot can be okay. Okay, and we did this in sim. All those results were sim. This is showing it running on a real robot, but I don't have time to show the video. Okay. Okay, so we talked about POMDPs and stuff, and I will stop here because you said to stop at 5 of, or actually 10 of or 5 of. So I'll pick 5 of and only be 3 minutes late. We have lots of other cool stuff. This is robot writing. It's seeing the bitmap image from the top half of that screen, and then it's producing a policy to draw it with a pen on the bottom half. Thanks. Yeah. I'll pretend you're all clapping. Here's my very patient son. I can take questions.
Ankit?
Hi.
Cool,
So
thanks.
hi, I really like the idea of having some sort of a robot formal language, but LTL might not be it. So what more are the requirements from formal languages before we can think of them as mapping to natural language?
Yeah, we actually were, I don't know. I would love examples of commands that LTL can't do. We did this exercise when I was a postdoc in mixed group where we like brainstormed commands and tried to think of, like, it was like us as roboticists trying to think of things that we might like to say to the robot. And many of the commands, the LTL kind of commands, the avoid commands and stuff, came from that. Like at the time we were like, I have no idea how to do them. And now I'm really excited we can do them. But I kind of checked off everything on my list in that space. I don't think that's really true. I think there are more commands that we need. But the pressing things on my list now are all about POMDPs. So what to do in partially observed environments. So we're thinking about stuff like find the car behind the building, but avoid the main square, where you might not know where the car is in advance. And maybe you don't even know where the main square is in advance. And you have to make a plan to find those things and then avoid them, avoid them if you're supposed to avoid them. And maybe make guarantees about minimizing regret. Because of course, if you don't know where the square is, and your detector has limits, you may not be able to avoid it in general. So what we're trying to do now is really move to the POMDP setting, because I think that's where the big challenges are now.
I guess I have a follow-up question, if you don't mind. Have you looked into integrating CTL in addition with LTL? Like if you wanted to say to a robot, I never want you to go to this place, or I never want you to fly lower than a certain height. What's
CTL?
It's computational tree logic. It's actually a superset of linear temporal logic, and it incorporates quantifiers. Sorry, it incorporates quantifiers on top of LTL.
Oh, I see. So if you don't know what the landmark is,
yeah. So for you to say, instead of just saying one command for and express a constraint for one particular path, you can express a constraint that can say cover all potential paths in the future. Like for all the trips that you want to make to the shipping container store, I don't know, you can say, I never want you to take this particular highway, or I never want you to fly above this area. Has there been any work in that aspect?
No, but I think that's really interesting, and I would love to learn more. I think that's a great idea.